All right, so now we're going to take a look at the examples in this set of notes that will look at applications of both the fundamental theorem of calculus part 1 and 2, as well as the mean value theorem for integrals. And we're going to start with the mean value theorem for integrals. Okay, remember that you still, when you're doing these, have to make sure that conditions have been met to invoke a theorem. Your condition for MVT for integrals is that you have a function f that is continuous. It only needs to be continuous because if it's continuous, that means that f is integrable, which is what we need for integrals. So of course we have a polynomial which is continuous, so we know that we can integrate it. So the mean value theorem for integrals says that at some point, if I were to calculate the average value of the function, and the average value of the function using 1 over b minus a times the definite integral, that at some point in for some c in a to b, that the average value of the function is in the interval somewhere, all right? So we first need to calculate the average value. So I'm going -1 to 2. So I actually calculate the value. So that's going to be 1 over 2 minus -1, integral -1 to 2 of 1 plus x squared dx. We go ahead and we calculate this. This ends up being 1/3. We're doing a definite integral, so we're going to calculate the net change or the accumulation. I'm going to find my antiderivative, so I'm going to end up with x plus x cubed 1/3. I'm doing a definite integral, so I show that I'm evaluating it -2 to 1. We calculate our net change by plugging in our values, so we do 1/3, 2 plus 8/3, minus 1/3, plug in our -1, -1 minus 1/3, and we get this value. Okay, we're still not done yet at this point. I'm just finding the average value at this point. So we do some arithmetic here, and I'll leave you to verify, but this ends up being 2. So the average value on the interval from -1 to 2 is 2, and then after we find the average value, so that's like step 1. Step 1, find the average value using your formula. Now step 2, find c, solve for c. So I take my function f of x and I set that equal to my average value, and then I just solve. And this is nice because you're just going to end up with x squared equals 1, x equals plus or minus 1, and then you choose the ones that are on the interval, and they're actually both on the interval. So the values of c guaranteed by the mean value theorem are x equal to plus or minus 1. That's what we're looking for in this problem. Step 1, find your average value. Step 2, set it equal to your function and solve for c. When we were doing the mean value theorem for derivatives, step 1 was find your average rate of change, and step 2 was set it equal to your derivative and solve for c. So those are the two steps that we're looking at. All right, and then this I talked about in the last video, but it bears repeating. Show that the average rate of change of a car's position over the time interval. Okay, so let's define s of t is my position function. Okay, so the average rate of change of s of t on the interval from t1 to t2 would be s of t1 minus s of t2 all over well actually we should do t2 minus t1, t2 minus t1, okay? So that's our average rate of change of the interval, and then we want to show that that's the same as the average value of the velocity function v of t. All right, over the same interval, t1 to t2. So the average value is found by doing 1 over t2 minus t1, definite interval, t1 to t2 of v of t dt. Now, how do I prove that this is the same as this? I apply fundamental theorem of calculus. I go ahead and say, well, if I wanted to calculate this definite integral, I would find the antiderivative or an antiderivative. And isn't the antiderivative, couldn't we think of this as my position function as the antiderivative? So I can calculate my net change in the antiderivative, the position function, s of t2 minus s of t1. That basically what I'm doing here is finding an antiderivative and evaluating it from t1 to t2. That's what you're doing when you do this definite integral. So I calculate my net change, and clearly this is exactly the same as the average rate of change of the position function. So knowing that these two things are equal is going to be an important point. And like I said, how do I know whether I want to calculate the average of the velocity function by doing this formula or using this formula? Depends on what you're given. If I know the position function, I do this. If I know the velocity function, I would do this. All right, so let's take a look at the next example. This is an idea where we have a table of values. It does tell me that we have a continuous function, so I know that I can integrate. And it's going to ask me for a couple of things here. It first wants me to find the arithmetic mean, so maybe we need to think about what the arithmetic mean is. And then we're going to use a trapezoidal approximation to estimate the average value of the function on 20 to 50. And then they're asking some questions about which is more accurate, is one method better than the other. We'll talk about that. All right, so let's calculate our arithmetic mean. Arithmetic mean is simply add up the numbers and divide by how many you have. So our arithmetic mean of f of x, the y values, would simply be me taking 42 plus 38 plus 31 plus 29, 35, 48, and 60, and then dividing by the number that we have, 1, 2, 3, 4, 5, 6, 7, and divide by 7, which we get 283 divided by 7, which is approximately 40.429. 40.429. Let's see if I can get that in there. All right, so now we want to use a trapezoidal approximation, which basically means, because when we're trying to find the average value of f, okay, let's come over here, average value of f, we know that we're going to do 1 over b minus a, the integral a to b of f of x dx. And since we're going 20 to 50, so this average value is going to be 1 over 30, your integral from 20 to 50 of my f of x dx. And so that's where the trapezoidal approximation is going to come in that what I need to do is I need to figure out what this definite integral is. And I can't find it exactly because I don't have a formula like we did above. So what I'm going to do is I'm going to estimate this using the trapezoidal approximation. So I am going to, the nice thing about this, if we check here, all of our intervals are equal widths. So we're going to use a delta x equal to 5. And remember, we're going to have to do a left sum and a right sum. So maybe we'll come down here and we'll show our work for our approximations. Our left sum, and we'd have 1, 2, 3, 4, 5, 6 rectangles. Our left sum would be our delta x times the left endpoints, so the heights using the left endpoint. So I'd start over here, 42, 38, 31, 29, 35, and 48. My right sum Delta x is 5. Now I use my right endpoint heights. So that would be my 38 plus 31 plus 29, 35, 48, and 60. And then remember that what we're going to do for our approximation, just showing the work here, I would say that this is approximately 1 over 30 times T4, which is going to be 1 over 30 times my left sum plus my right sum divided by 2. Average my left and my right. So we're just going to pick up our calculator and we're going to do those calculations. All right, and as you can see, I didn't make you sit there while I calculated. Adding this up, we got 1,115. This one we got 1205, and then I just plugged them in and calculated my average value. Now, of course, you got two different answers. There's two different estimates of the average value of the function, and so the question might be, is one more accurate than the other? What do you think? What do you think about which one is more accurate? Now at this point when I ask this question, I wish I could have like a button for you guys at home and you could say, hey, we think this is the better method. But let's kind of talk about this. The arithmetic mean, when we're trying to use that to estimate what the average of the function is, we're only using these individual values in order to calculate it. All we're doing is adding up basically 7 of the infinitely many values that you have. And so that's maybe not a great estimate. Depends on which values you pick. Maybe you didn't pick some very good ones as your finite number that you're going to add together. When you take a look at your trapezoidal idea, that we have this formula for the average value of our function, and we really just need to have the area under f of x and then times our 1 over b minus a. That if you think back to the picture of the trapezoidal approximation, that the trapezoid is a very close estimate to the area under the curve. So when we're looking at this, this idea of using our left and our right and then averaging together, this actually gets a fairly good representation of that area under the curve, which then multiplied by 1 over b minus a will give us what we feel is a good representation of the average value of f. So in terms of determining which would be more accurate, I mean, you wouldn't definitely know until we actually had the actual value and made a comparison. But if I had to guess which one would be more accurate, I would go with the trapezoidal rule and the trapezoidal approximation. And then is one method better practice than the other, I would definitely use the trapezoid because on the AP test, that's the one that you're going to be using the most. Okay, now looking at the next example, the idea that we can use the fundamental theorem of calculus where we end up with a function instead of having values that you're actually going to calculate is going to be important. That you want to be able to work with these integrals as formulas as well. So let's look at example 16. We want to find a number b such that the average value of this function on the interval 0 to b is 3. So we're telling you the answer, and so your job is to basically recognize that the average value of f on your interval from 0 to b, you can use the formula 1 over b minus 0, integral 0 to b of f of x dx, and we know that that is equal to 3. So what we're basically going to do is solve the equation 1 over b. We're going to actually calculate our definite integral because, you know, we've learned some shortcuts at this point. And we are going to set that definite integral after we calculate it equal to 3. So now let's go ahead and calculate this. The antiderivative, so I'm going to bring down my 1 over b. Maybe I'll put a so we know that I'm starting my problem here. So I have 1 over b. I find the antiderivative, 2x, x squared, 6 divided by 2 would be 3, minus x cubed, oh how nice, that would just be x cubed, and we're evaluating a definite integral from 0 to b. Remember it's equal to 3, so I'm just bringing that down. I now calculate that, so we have 1 over b times plug in b, 2b plus 3b squared minus b cubed minus 1 over b times 0, because you're going to plug in 0, and this is equal to 3. And hopefully you can see that all we're doing is just simplifying and solving at this point. This part's going to go away, and over here we're going to have 2 plus 3b minus b squared is equal to 3. And why don't we just get everything on one side, minus 3b and subtract 2 plus 1 equal to 0, and then all we have to do is solve for b. It's not something that factors, so we can use our quadratic formula, and once we use our quadratic formula, then we're pretty much straightforward and going to get our answer. Alright, so using the quadratic formula, our b would be equal to 3 plus or minus square root 9 minus 4 times 1 times 1 all over 2, which is going to give us 3 plus or minus square root of 5 all over 2. But remember, the b value that we're looking for, if I come back up here, we're looking for the number b on the interval 0 to b, so that you get the average value equal to 3. So we're, when you look at this, does it really matter? I guess technically we're assuming that b is greater than 0 here, because we're going 0 to this value. So when we take a look down here, I would choose that the b value is going to be the 3 plus square root of 5 over 2 would be what would make the most sense in this problem. All right, let's take a look at the next examples that we have. So we're just practicing with solving these equations. So we end up with some values here. We're going to have some definite integrals that we're going to need to calculate. And this is the idea of using fundamental theorem of calculus, that we can come up with this accumulation function from this by performing the antiderivative. The antiderivative of t cubed would be t to the 4th, 1/4, minus t squared, 7/2. And we're evaluating this definite integral from -5 to x, and of course it's equal to 0, because we have an equation that we're working here. We plug in our x, so we end up with 1/4 x to the 4th minus 7/2 x squared, and then we have to plug in our 5. Remember, you're doing net change, so minus my 1/4 -5 to the 4th minus 7/2 -5 squared, and that's equal to 0. So let's do a little simplifying here. So we're going to get 1/4 x to the 4th minus 7/2 x squared plus, after I multiply this out and add it up, I get 275 over 4 equal to 0. And then I'm just going to multiply both sides by 4 just to make this into a nicer problem. So x to the 4th minus 14x squared, and then plus 275 equals 0. This is kind of like a u substitution. You can think of this as x squared and then apply your quadratic formula. So 14 plus or minus square root 14 squared minus 4 times 1 times 275 all over 2a. So we're going to calculate those values. Alright, and then as always, I always feel like somebody needs to be yelling at me on the screen when I make a negative mistake. I always find it, but it's always when I get to a point I start to calculate something and I think, oh, wait a minute. That's a negative here and here because I'm subtracting the value that I had. So that should be minus 275. So we'll add that in. All right, and so we could solve, we could get these values, all right, using what we have on our calculator, and then after I get that value that goes here, I'm going to do the square root and plus or minus that. One comment that I do want to make about kind of solving it from this point, we're just using algebra, we actually should know two answers to this before we even start. And intuitively, you should be able to think about the fact that, well, first off, what would be a value for x that if I start at -5 and I want to accumulate my area, that would be an obvious one that jumps out that would always have an accumulation of 0? Well, hopefully you guys shout out -5, because if I start at -5 and I don't go anywhere, then I can't accumulate any area to have. So we know that -5 is going to be one of our solutions. Another thing to look at with this function is to notice something important about the f of t that we're graphing and doing this accumulation of error, is that this is t times t squared minus 7. So it goes through the origin, and then it goes through square root of 7 and negative square root of 7, but that this odd power function that I'm graphing is an odd function. So it should be coming in, turning, and then kind of coming back out in this direction. So kind of our accumulation of area, and of course we're accumulating from wherever -5 is here, that because it's odd, that whatever I accumulate on this side will then be taken back out on this side, because you're always opposite in signs there. So hopefully you could see that x equal to 5 is also an intuitive answer to this, because we have an odd function. And so as long as you are equal balanced around the origin, the accumulation of area is going to be 0 as well. So those are going to be two solutions. Now the question would be what the other solutions are going to be. So let's go ahead and finish this out and see what happens. So this actually ends up being 14 plus or minus 36 over 2. So that's going to give us 25. Oh, just like we expected, there's our plus or minus 5. Or we're going to have 14 minus 36 divided by 2 is going to give us -11. And then we find out that there really aren't any other places that are there. That technically there would be 4, but because I now have x squared equal to -11, that there are no solutions for this. So actually, we had the two answers just by intuitive understanding, but we've done the work, the calculus behind it, to prove that there are only two answers. All right, so now let's take a look at our second part over here, our idea of what we're trying to do on this one. So on this one, as we are accumulating our area, okay, from -3 to k, we're on a parabola this time. So maybe let's start with a sketch and we'll get the intuitive answer first. So we have our x squared minus 4, right? We have down here at -4, we're going to cross here at 2 and -2. And so we're starting back here at -3. And so we are looking at the accumulation of area. Okay, so we would be -3. Now what's one intuitive solution that the k is going to be? We know that k equal to -3 is going to be one answer. And then we take a look at this, and if we start kind of estimating that there are going to be some other places where there might be some answers, well, sure, if I accumulate some and then at some point I'm going to take it out, I don't know where, so maybe somewhere in here there might be an answer, okay, where these areas are equal to each other. So I'll put a star right there, and then we'll start to subtract out a little bit more here, and then we'll add a little bit more back in, and then maybe there's another answer somewhere around here. I'd say if I had to guesstimate that there's probably another two answers besides this one. Once I get past here, I'm just going to continue accumulating so that it's not going to come back down to 0. So you can sometimes reason out how many answers that we're going to have. But let's go ahead and actually work through the calculus process. Let's find our antiderivative. 1/3 x cubed minus 4x. We're evaluating it, doing net change from -3 to k, and we want to know when is it equal to 0. We plug in our k value, 1/3 k cubed minus 4k. Then we plug in our -3 so we can calculate our net change. So 1/3 negative 3 cubed minus 4 times negative 3. Of course, this is equal to 0. We do some arithmetic here. This is negative 27. This would be negative 9 minus plus 12. Negative 9 plus 12 is 3. So we get 1/3 k cubed minus 4k minus, okay, let's just double check our math here. This was negative 27 divided by 3, negative 9 plus 12, okay, which would be minus 3, equal to 0. And then maybe make this a little nicer. Let's multiply everything by 3. So k cubed minus 12k minus 9 equal to 0. Now at this point you may be going, oh, that's a cubic. It's not something I can use quadratic formula on like I could over here. But remember, we know from common sense what one solution is, negative 3. And so we recall our synthetic division from our Algebra 2 skills that I already know one answer, so I'm going to go ahead and divide that out. I'm going to take my negative 3 and divide it through. Our coefficients would be 1, 0, negative 12, negative 9. And using our synthetic division, we drop our 1, negative 3, we add, we multiply, 9, we add, negative 3, 9, we add, we get 0. And that gets me down to a factor of k squared minus 3k minus 3. And so now I can set that equal to 0 and just solve using quadratic formula. So we would have k equal to 3 plus or minus your square root 9 minus 4 times 1 times negative 3 all over 2, which would give me 3 plus or minus the square root of 9 plus 12, or 21 all over 2. So we actually end up with our solutions, 2 more that we're looking for, of k equal to 3 plus or minus square root of 21 all over 2. And so those would be the 3 values that are going to give us an accumulation of 0. Alright, so now let's take a look at the next example, and this is important, okay, so I'm going to underline this one. This is something that you're going to be doing a lot of on the AP, this idea that we're going to go back to our differential equations, where I have given you a derivative, and I've given you an initial condition, and I'm going to ask you to find f of 2. By first, we're going to find a particular solution to the differential equation and then evaluate the solution at x equal to 2. This is what we did back in section 5.1. And now what we're going to do is we're going to show the relationship between finding this f of 2 using a definite integral and using the net change. Alright, so going back to section 5.1, we know that we can find a general antiderivative by taking the antiderivative of 2x squared minus 2 dx, that if I were to find this general antiderivative, I know it's not a definite integral because there's no bounds, I would get my add 1 to my power and divide, so that would be 2/3, minus 2x plus c. Okay, so that would give me my general antiderivative. And then I'm going to use the fact that when I have this general antiderivative, f of x equal to 2/3 x cubed minus 2x plus c, now I'm going to use the initial condition f of 0 equal to 5 to find c. So I plug in my 0. We end up with 2/3 times 0 cubed minus 2 times 0 plus c, and that's going to give us 5. So c is equal to 5. So that tells me that my actual specific antiderivative, remember that this was my general antiderivative. Now I found a specific antiderivative based on the fact that I was given the initial condition when f of 0 equals 5, I found the specific antiderivative. I got 2/3 x cubed minus 2x plus 5. And then the next part of this was, hey, find f of 2. So f of 2 on this specific one would be 2/3 times 2 cubed minus 2 times 2 plus 5, and we simply calculate our value of that. So we end up with 16/3 minus 4 plus 5, and so we end up with 6 1/3 or 19/3. Okay, so that's fairly straightforward. That's what we talked about in section 5.1. So now we're going to do this a different way. Now that we've learned about definite integrals and the fact that definite integrals are net change, we're going to use this idea that to figure out f of 2, f of 2 is going to be where I was. Now this is kind of slang, but I'm going to put it in here. It's where I was at some point plus the net change from that point. Where I am is equal to where I was plus the change from that point. And if you think about what we're talking about here, what we're basically saying is that we can always find a function value by taking where I was, which is f of 0, and adding to that the net change from 0 to where I want to currently be on f of x dx. That I can set up this formula to find any function value I want, given that I know where I was at some point, and then I calculate the net change from that point in time to where I want to be. So we can calculate this by then plugging in our 5 and then calculating this definite integral instead of an indefinite integral. And hopefully you see that they are very much related to each other. So we take our integral from 0 to 2. We're going to put it in our function, which is 2x squared minus 2 dx. And then we would calculate an antiderivative. So we would take the, and do you see that these are very much directly related procedures? One's using indefinite, one's using definite in order to find the same quantity. So this is going to be my x cubed 2/3 minus 2x, but because I'm doing net change, I'm going to put in that I'm evaluating that at a net change of 0 to 2. And notice I'm not even really worried about what the constant is in this that I was worried about over here. Here I'm actually just directly calculating it. So it'd be 5 plus, and then we plug in our 2. 2/3 times 2 cubed minus 2 times 2, and then we subtract our plug-in 0, which is going to be 0, and you'll see that this does end up being the same 19/3 that I found earlier. So basically with these two processes, you can have this idea of where, in order to find out where I am at f of 2, given an initial condition, I can actually find the general antiderivative, calculate the constant using the initial condition, and then calculate f of 2. Or I can directly calculate f of 2 by taking where I was and adding it to the net change that occurred from where I was to where I currently am. Now this is going to be important because there will be times where we may not be able to find a general antiderivative, but yet we have information that will allow us to calculate this definite integral. So we are going to kind of practice using this method quite a bit because it's very important. This will come up on the AP where I'll need to know that I might not be able to use this process, but I can do this by either estimating this definite integral with maybe a trapped sum, or I will have information in area under the curve that I can use to calculate it. All right, so like it says here, in the previous example, the first method relies heavily on our ability to find the antiderivative. And that's not always easy, possible, or something that we want to do. So if I want to find a particular value in the solution of a derivative, then what we're going to do is instead figure out where you started and then where you've gone, which is your displacement, that's your net change. So take where you were and add to it how much you changed from where you were. So we're definitely going to use this idea of finding your net accumulation or your net change with a definite integral and adding it to where you currently were at any point in time. And so that's always going to be important. So this is our most important idea of accumulation that we are going to use it pretty much guaranteed in a free response, which is that where I am now is what I started with plus what I've accumulated since I started. And so this formula is something that you are going to use quite a bit. And so we're going to practice with that. All right, so let's take a look down here at example 19. So each of these times, what I'm going to do is all I want to do is using my calculator. So that means I don't need to actually find an antiderivative, which would be the long way like method A on the last example, that all I need to do is set it up and then use my calculator to find it. So here, for example, in A, I want to find f of 3. Well, I know where I was at f of 2, and so then all I need to do is calculate my net change from 2 to 3 on f of x dx. So what I'm going to type into my calculator is going to be the negative 2, where I was, plus 2 to 3, 4 sine squared of 2x dx, and I'm going to use that on my calculator to get an answer. Okay? I'll do all the calculator once at a time. I'm going to write them all down and then I'll come back and put them in. If I want to figure out where I am at time x equal to 5, I take where I was plus my change from where I was to where I currently am. So I calculate my net change. So in my calculator, I would type in negative 2, 2 to 5, 4 sine squared of 2x dx. Okay. Then I can come here to C, f of negative 2, again, where I was, plus my net change from 2 to negative 2 of f of x dx, which is going to be negative 2 plus 2 to negative 2. And it doesn't really bother me that I'm going backwards in the interval. It will work out, because working backwards means you just do the opposite instead of you kind of deaccumulate going through your interval, and we could find that value. And then notice here in part D, it says write an integral equation for f of x. So just keeping that in mind, we know how to find the actual solution by taking our f of 2, which is negative 2, and adding that, the integral from 2 to x of f of x dx. Notice that we take where we were plus our accumulation function that we defined using the fundamental theorem of calculus in this section. That is the key idea of how you're going to find a specific antiderivative using your accumulation function and where you were. Okay? Now let's just go ahead and calculate each of these. So I'm going to pause the video, give you a chance to calculate these on your calculator, and then we'll come back and verify. And we'll also kind of show a graph of this and show what it looks like on your calculator as well. Okay, so coming back in and just taking a look at the values that you would get, notice basically what I did is in my y equals, I typed in the function that I was given as the integrand of my function, and then I basically just went to the home screen and I said where I was, and then 2 to 3, 2 to 5, 2 to negative 2. So that gives me these values that we're looking at. All right, and so our general formula, I'm going to go back to my y equals, to get the specific antiderivative given that initial condition, what I would basically graph then is I would get rid of this, and if I wanted to actually graph it, I would take my negative 2 plus my definite integral, my accumulation function, so math, and we choose number 9. We're going starting from x equal to 2, that was where our initial condition is, up to x. And then we're going to put our y1 here. So vars, yvars, function y1. And x. Alright, so and after we've put that in our y equals, and again just to show you what we had in there, so I took where I was plus my net change from where I was to where I want to go, and I put an x here, and then put my function in, and it will take a while for this to graph. I'm just not going to lie to you, I've been sitting here with the video paused for quite a bit, but here is the curve that we're looking at, and if I hit trace and I type in my 2, that will show me that, oh look, this has a value of -2, which is the where I started from. And then if I type in 3 and enter, we're going to get 0.7629, okay? So remember that from our home screen, 0.7629 is what we got earlier. And then if I take and type in my 5, so if I hit trace and 5, then you would end up here at your 4.0382, which again, if we check on our home screen, 4.0382. So those are the values that we found by doing this idea. Where I currently am equals where I was plus the net change to where I want to go, from where I was to where I am now. So that is this is the big idea, that you can create this function. You can find a specific antiderivative function by taking where you were plus your accumulation from where you were. And that's this main idea about the fundamental theorem of calculus. That's why we had that part 2, which is not only is a definite integral a net change, that we can use the definite integral as a function that will give us an accumulation function that we can use to find the original specific antiderivative given an initial condition. And you can also see that what you can do in each of these, depending on where you start from, like maybe the initial condition is not at 2, you're at -2. What if you were at, say, -1 instead of -2? You will get another specific antiderivative that has a different starting position. So I'm just going to go back in and put the value in. So now I'm basically calculating, given that I started at a different location than what I had. And hopefully you'll see when we do this that it's going to be nothing more than a vertical translation of the graph that I have currently in there. Now I'm going to pause the video while I do that, because this is probably going to take quite a long time to graph, and you can play along with me as we do it, but we'll go ahead and we'll hit graph again, and we'll start to see slowly but surely the graph coming along here, and notice that it's going to be exactly the same as the one that I already have graphed. It's only going to be shifted a little bit. And what's going to be the shift of what we're looking at, you'll see here at 2, it was -2, okay? So when we come up here, now it's going to be exactly 2, -1, because I have a different starting position. But my accumulation function is the same, I just started in a different place. All right, so I'm just going to pause this so you can see the final result, and then I will continue on with the next example. All right, and as you can see, after I've let this thing run all the way out, that this is another specific antiderivative given a different starting point. And so I could continue changing my starting point and sketch several of these across and get the whole family of antiderivatives by looking at that. But I just wanted to kind of show you the difference. So the big idea, the main important thing that you want to talk about here is that if I want to figure out where I currently am, I have to know where I started from and the accumulation from where I started from, my net change. And that if I know that, I can set which specific antiderivative that I am on. So this, like I said, I cannot star this fact enough, that you always have to remember that where I am is where I was plus my net change. All right, so now let's take a look at this one. So we're doing the same thing here. We're basically saying you're given a derivative, and you know a starting value, and you want to find g of 2. So again, we are not going to do it the long way using the differential equations, find the general, find c, and then plug in, and after you get your specific one, and plug in 2. We're just going to go g of 2 is going to equal where I was, g of 2, plus my net change from 2. Oh, wait a minute. When I don't even really need to do any work for this one, do I? Because where I am is where I was plus my net change. Well, what's my net change? 0. Oh, that one we know. The answer is simply negative pi. So I could have done that without writing this definite integral down, but I've got that answer, so we're good to go. Now we're going to do g of pi. So g of pi is going to be where I was when I was at g of 2 plus the change from 2 to pi on my e to the sine x dx. So my where I was plus my net change. Okay. So we're like, okay, I'm going to I'll calculate this on my calculator. We'll do an approximation here in a second. And then g of 0, I'll put this down here for the interest of room. G of 0, again, where I was, plus the integral from 2 to pi e to the sine x dx. Notice this does not require that I actually know how to calculate this definite integral. That's why it's the beauty of this, that I can calculate these without having to know how to integrate this, because that obviously looks like a really complicated integration because it has a chain rule and a composition involved in it. Alright, so let's go to our calculator and calculate each of these. Alright, so I've typed them into my calculator, where I was, my net change from where I was to where I want to go, and then we have our values here. So that should be fairly straightforward in terms of calculating those for us. Alright, so now taking a look at our last example, example 21, is again this idea, as long as you remember when you're looking at your application problems on the AP, that where I am can be found by taking where I was plus my net change, then when you hit the free response problems, it should be fairly straightforward. So we're saying at the start of Christmas break, a man weighed 180 pounds. So at his weight, W of 0, was 180 pounds at the start of Christmas break. We know that his rate function, he is accumulating at a rate of 10 sine pi t over 8 pounds per day. Pounds per day. All right, units are going to be important too, kind of as we are dealing with free response questions. We might want to pay attention to what our units are. And we want to know what was the man's weight at the end of the break 14 days later. W of 14 equals what? So where I end up at 14 days equals where I was plus my net change from 0 up to day 14 of my rate function, dt. So this is essentially what we're going to use for our setup. And then we'll just use the calculator to estimate what this is. So we'll type it into our calculator. All right, and so after typing it into our calculator, we see that our 180, where we were, plus our net change from 0 to 14 days is going to give me 187.458 pounds, or a difference of added 7.5 pounds to the person's weight. So, but don't judge. So hopefully you've seen that 0.45, and because we're AP and we go 3 decimals, 458, we'll put that down, pounds. And so the idea here is to recognize what we're actually doing. Now also in terms of units, knowing that you're taking pounds plus your net change in pounds is going to give us a units of pounds here as well. And so this idea, if you can understand the key concept, where I currently am equals where I was plus the net change that occurred between where I was and where I am now, you will be fine on the AP. All right, so that wraps up the examples for section 5.4. So we'll begin the next section, which is we've also haven't really learned about some harder problems where we're trying to find antiderivatives when we have a chain rule involved. So that will be the next section.